either R or RC circuitry or by UJT relaxation oscillator we can turn on the SCR. So let us discuss one by one. So first method is nothing but R triggering. Circuit diagram shows you the method of triggering the SCR by help of a resistance. Here you will observe that a load is connected across SCR in series with an SCR, and the gate pulse is provided through resistance R and R1 and R2. Now the voltage across gate terminal VG totally depends upon the value of R2, and by varying R2 we can control the gate voltage which is applied across the thyristor, and by controlling the gate voltage we can control the turn on of SCR. So you can observe here in the waveforms that we are considering a case where R2 is very high. If R2 is very high, in that case the voltage VG will be very small, and because of which current flowing IG will be again small and will not be in position to turn on the SCR. So SCR will remain in off state, and you are observing here that V0 and I0 both are 0, means nothing but voltage across load is 0, whereas current flowing through load is also 0, as SCR is in off state because current IG is not sufficient to turn on the SCR. So this is nothing but first case where we are assuming that the value of resistance R2 is very high. Now if we take a next condition, that is R2 is an optimum value. So if we go for R2 is equals to optimum value, at a particular voltage we will get a sufficient amount of current which is given across the gate terminal, and when we apply the sufficient amount of gate current to the SCR will turn on, and here you are observing the waveforms of applied voltage Vs, then which is sinusoidal signal, then you are observing here Vg which is nothing but an gate voltage and which totally depends upon value of R2, then you are observing VO is nothing but the output voltage VO, and you will observe that till I am applying IG or VG, the SCR will be in off state, and when SCR is in off state, output voltage V0 is 0, whereas when SCR turns on, whatever voltage applied across will be available across the load because SCR will be acting as a closed switch. And you can observe the waveforms of I0 and voltage across thyristor also. So V0 and I0, the waveforms are same because we are assumed that the load is resistive. Means when load is resistive, the waveforms of voltage and current will be same, only the difference will be there in the magnitude. The third case we can see with the help of resistance value R2 is very small. If R2 is small, we can comparatively earlier trigger the device or we can turn it on. Means by valuing, by considering all these three different cases, you will observe that R very high, we cannot turn on the SCR. If R2 is very small, we can turn on the SCR earlier, whereas if R2 is moderate, we can turn on the SCR at a moderate time. Means nothing but this firing angle alpha where the SCR turns on can be controlled by varying the value of resistance R2, and that's why this method is called as a resistance triggering. The advantages of this triggering is the circuit is very simple. The construction of the circuit which is used in case of triggering is very simple, but it suffers with a limitation that we can control the firing angle up to 90 degree only. We cannot control a firing angle alpha beyond 90 degree, as you are observing that the sinusoidal applied signal is sinusoidal. It will go to its maximum peak at alpha is equals to 90 degree, means it will reach to its maximum value Vm at alpha is equals to 90 degree, and SCR will maximum we can turn it on up to 90 degree. We cannot control firing angle beyond 90 degree. So this is limitation of an R triggering. And one more is that is nothing but we cannot get the precision firing angles. That is again one second drawback of an R triggering. And here in case of R triggering, we are controlling only one parameter of the signal, that is nothing but the amplitude, and because of this these two limitations are coming. You can observe with three waveforms, that is nothing but one in case of R2 is very high, next is R2 optimum, and next is R2 is very small. So here suffers with the two severe disadvantages, that is nothing but we cannot control the firing angle beyond 90 degree, and the second drawback is the precision control is not possible because we are controlling only one parameter, that is nothing but magnitude of the signal. We can switch over to the next method, that is nothing but RC triggering, where resistance and capacitance are used in the triggering. Here you are observing the circuitry that the gate signal which is provided is applied through resistance R and capacitor C. So by controlling either R or C, we can control the RC time constant. And by controlling the RC time constant, that is charging and discharging period of capacitor, we can control the applied gate signal across the thyristor, and hence we can control the total on and off process of the SCR. So here you will observe the waveforms at for is high. Means if R value is high, RC time constant is more, and as RC time constant is higher, you will observe here that SCR fires at an lateral angle. Now if I want to fire SCR at an earlier stages, I can reduce the RC time constant. RC time constant can be reduced either by reducing resistance value or by reducing capacitance value. And as you are observing here in the circuitry, that we can either vary either we can vary R or we can vary C. But here we are preferring to vary resistance value, and by varying resistance we can vary the RC time constant, and by varying RC time constant you are observing here that depending upon charging and discharging period of capacitor, we can vary the gate pulse which is going to be produced across the gate terminal, and accordingly which can be used to turn on the SCR. And you are observing here the waveforms of voltage across thyristor and the output voltage. Again here you will find the same thing, that when SCR turns on means nothing but whenever a sufficient amount of gate current is applied to the gate terminal of an SCR, so SCR will turn on, and when SCR will turn on, the voltage, whatever voltage applied, positive voltage applied will be coming across load, and voltage across thyristor will be very small, that is nothing but the onset voltage. And vice versa, when it is reverse bias, you are observing here in the negative cycle that when the SCR is in reverse bias, even though it applied on gate signal, it will not turn on, and voltage across thyristor will be the maximum voltage, that is nothing but the applied voltage. You are observing here, it is coming across the SCR. About the silicon controlled rectifier, the important member of the thyristor family. Whatever we have studied, from that we can conclude that silicon controlled rectifier is a unidirectional device. Means it allows current to flow only in one direction, that is from anode to cathode. So we can control only positive cycle by using silicon controlled rectifier. Unidirectional control is possible with the help of SCR, but bidirectional control is not possible using silicon controlled rectifier. So we'll switch over to the next component of the thyristor family, that is nothing but triac, TRIAC. Triac is nothing but it is two SCRs connected in an anti-parallel manner. Similar way, we can consider this triac as two SCRs connected in anti-parallel manner. One can conduct in forward direction, whereas other can conduct in reverse direction. So triac is nothing but it is a bidirectional device having three terminals, that is MT1, MT2 and gate. Right side of the slide you are observing the symbol of the triac. Here you will find that two SCRs are connected back to back in an anti-parallel manner. MT1 and MT2, these are the two terminals which are called the main terminal 1 and main terminal 2, and gate is the terminal through which the current flow from MT1 to MT2 can be controlled. Now as I said, it's a bidirectional device. It is possible for current to flow from MT1 to MT2 as well as from MT2 to MT1. Means here you will observe that current will flow, or it is possible MT2 as well as from MT2 to MT1. Now if we see to the construction of an triac, triac is nothing but it is a multi-pellet PNPN structure. It consists of P1, N1, P2, N2 and N3, N4 layers. So you are observing here the structure of a triac, that is the terminal MT1 is connected to N2 and P2 terminal, or N2 and P2 material of triac, or N2 and P2 layer of a triac. MT2 is connected for N4 and P1. It is taken from P2. So you will observe that every terminal is taken from two different types of layers, and the total layers are P1, N1, P2, N2 and N3, N4. So this is nothing but the construction of a triac which can operate in both the direction, that is positive as well as negative direction. So correct means operation in quadrant number 1 and operation in quadrant number 4 is possible in case of triad, which was not true in case of silicon control rectifier.